Welcome to your AP Statistics lesson on Chapter 26, chi-square test of homogeneity and independence. They are conducted very much the same way, so we will discuss these two in the same video. All right, comparing observed distributions. A test comparing the distribution of counts for two or more groups on the same categorical variables is called a chi-square test for homogeneity. So it's not that you've got one group or one set of individuals and you've got a bunch of categorical variables for them that you've summarized in counts, and you want to see how well those counts fit some theoretical distribution. Now you've got two separate groups and you've got one categorical variable, and you want to see if the distribution of that categorical variable is the same between the two groups. So a test for homogeneity is actually a generalization of the two proportion Z test. It's just there's more involved to it. The statistic that we calculate for this test is identical to the chi-square statistic for goodness of fit. In this test, however, we ask whether choices are the same among different groups. In other words, like I said before, there is no theoretical model. The expected counts are found directly from the data, and we have different degrees of freedom, okay? Because there is no theoretical model, so the expected counts come from the data themselves. All right, the assumptions and conditions are the same as the chi-square goodness of fit test. So we're looking at counted data condition, randomization condition, and expected cell frequency condition. The counted data condition, again, is the data must be summarized as counts. It has to be categorical data to start with, and then you're summarizing them as counts. Randomization and 10% condition, we don't, as long as we don't want to generalize, we don't have to check on these conditions. It's good to make sure that the whole reason behind the randomization condition is that you want something that's representative if you want to be able to generalize. So just kind of bear that in mind. The expected cell frequency, again, the expected counts, not the observed counts, but the expected counts in each cell must be at least 5. To find the expected counts, this is important. Your calculator will do this for you most of the time, but you need to know how to do this. You never know when on a multiple choice question or, on a really well-worded free response question, the College Board forces you to be able to calculate an expected count. So you need to know how to do this. The way you get an expected count is for that particular cell, you take the row total and you multiply it by the column total and divide by the grand total. And that's how you get the expected count. What you're doing actually is you're just figuring out if all things being equal, if you just had one big group, how many individuals would be in that particular cell. All right, we calculated the chi-square statistic as we did in the goodness of fit test. Okay, it's still the sum of the squared differences between the observed and expected value divided by the expected value. In this situation, we have R minus 1 times C minus 1 degrees of freedom. So this is different. Okay, R is the number of rows, C is the number of columns, so you do R minus 1 times C minus 1 for this test. We will need the degrees of freedom to find the p-value for the chi-square statistic. All right, you still want to examine the residuals because that's going to give you an idea of why we reject the null hypothesis when that happens. For chi-square tests, we want to work with standardized residuals since we want to compare residuals for cells that may come from very different counts. So to standardize, we just divide the residual by the square root of the expected value. These standardized residuals are just the square root of the components we calculated for each cell with the positive or negative sign indicating whether we observed more cases than expected or fewer. The standardized residuals give us a chance to think about the underlying patterns and to consider the ways in which the distribution might not match what we hypothesized to be true. Okay, so let's look at an example. A random survey of autos parked in the student lot and the staff lot at a large university classified the brands by country of origin as seen in the table. Are there differences in the national origins of cars driven by students and staff? So we're comparing the distribution of the country of origin of the cars between two different groups, the student group and the staff group. So this would be a test of homogeneity. We want to see if they're distributed in the same way. That's what homogeneity means, that everything's distributed in the same way for the students as the staff. So we're going to write appropriate hypotheses. Our null hypothesis would be the distribution of car origin is the same. There's no difference for students and staff. And the alternative is that there is a difference. The distribution of car origin is different for students and staff. We want to check the necessary assumptions and conditions. So yes, we've got counts of cars. All right, they went through and recorded, looking in the student lot, American, American, European, Asian, American, 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 European, Asian. They do the same thing with the staff, and then they summarize with counts. Randomness and independence, it says it was a random survey of the autos, so that's stated. Expected counts using our formula that we had before, where you take row total times column total divided by grand total, you get 115.15 and so on. The beautiful thing is that most of the time we're going to actually let the calculator calculate that for us, but it wouldn't hurt for you to go back and use this here, the row total times the column total divided by the grand total, and see that you end up with these numbers. Okay, so if you do 107 plus 105 times 107 plus 33 plus 55 divided by the sum of all these numbers, you should get 115.15 and so on. So take a second and do that. Okay, so the calculator also creates a matrix called EXP matrix when you do a test of homogeneity. A two-way table test is how it's actually written in the calculator, and I'll show you how to do that in a minute. And then you want to find the p-value of your test. Okay, either on your scratch pad or on a calculator page in a document, create a 3x2 matrix. Why 3x2? Because we've got 3 rows and 2 columns. Okay, and enter the observed values in the matrix. Store the matrix in a variable. You can call it OBS for an abbreviation for observed, by pressing stow arrow and typing OBS and pressing enter. Select menu statistics stat test because we want to do a statistical test, and then choose chi-square two-way test because we're using a two-way table. Enter OBS when prompted for the observed matrix. Press enter. You should get a bunch of results, including your p-value of 0.01996. To see your expected value matrix, press the var key and select stat.exp matrix. Press enter until it appears on your screen, and then boom, there it is. All right, state your conclusion and analysis. So we're going to state the p-value, say whether it's small or large, and then either reject or fail to reject the null hypothesis, and then make a statement about evidence for the alternative, or the lack of evidence for the alternative in the context of the problem. So due to our low p-value of 0.02, we reject the null. There is significant evidence that the distribution of car origin is different for students and staff. Okay, now we're going to look at chi-square test of independence. It's also a two-way table test, and the mechanics are going to be very much the same as a test for homogeneity. The situation's just a little different, and so how we think about it is a little different. Contingency tables is another way of talking about two-way tables. They're considered contingency tables when they categorize counts on 2 or more variables so that we see whether the distribution of counts on one variable is contingent on the other, has some sort of relationship with the other. A test of whether the 2 categorical variables are independent examines the distribution of counts for one group of individuals classified according to both variables in a contingency table. So a chi-square test of independence uses the same calculations as a test for homogeneity. All right, so we still need counts and enough data so that the expected values are at least 5 in each cell. If we're interested in the independence of variables, we usually want to generalize from the data to some population. In that case, we'll need to check that the data are a representative random sample from the population. Examine the residuals. Each cell of the contingency table contributes a term to the chi-square sum. It helps to examine the standardized residuals just like we can do for a test of homogeneity. All right, Chi-square tests are common, and tests for independence are especially widespread. We need to remember that a small p-value is not proof of causation. Since the chi-square test for independence treats two variables symmetrically, we cannot differentiate the direction of any possible causation, even if it existed. We don't know which variable would cause the other one. And there's never any way to eliminate the possibility that a lurking variable is responsible for the lack of independence. So just because you find evidence that there is a lack of independence, that does not mean that that we've shown that one variable causes the other. In some ways, a failure of independence between categorical variables is less impressive than a strong, consistent linear association between two quantitative variables. So we can't even say causation there, so we certainly can't say causation here. Two categorical variables can fail the test of independence in many ways. Examining the standardized residuals can help you think about the underlying patterns because it can show you where the largest differences lie. All right, so what can go wrong? Don't use chi-square methods unless you have counts that summarize categorical variables. Just because numbers are in a 2A table doesn't make them suitable for a chi-square analysis. Beware of large samples with a sufficiently large sample size. A chi-square test can always reject the null hypothesis. Okay, again, that can happen. Don't say that one variable depends on the other just because they're not independent. And remember, association is not causation. All right, let's look at an example for our chi-square test of independence. A poll conducted by the University of Montana classified respondents by whether they were male or female and by political party, as shown in the table. We wonder if there's evidence of an association, that's another way of saying not independence, between being male or female and party affiliation. So is this a test of homogeneity or independence? Independence, we are taking a single sample, one sample, and testing for evidence of an association between two variables within the sample so that we can make an inference about the existence of an association between the two variables within the population the sample represents. So we're going to write appropriate hypotheses. The null is that there is no relationship or association between political affiliation and gender, or another way to say it is political affiliation and gender are independent. The alternative is that there is a relationship or association between political affiliation and gender, or political affiliation and gender are not independent. Note, we did not use the word dependent anywhere. In statistics, dependence means something more specific than lack of independence and is not appropriate here. Are the conditions for inference satisfied? Counts, and we want to know if we've got a random representative sample and if our expected counts would be greater than 5. Our counts are there. We have counts of respondents to a poll. Okay, so for each respondent, they made note of whether they were male or female, and they made note of whether they were Democrat, Republican, or Independent, and then they summarized all those responses with counts. So we're good to go. It's not stated that the sample was selected at random, but it's a plausible assumption to make. The sample may be representative of the population of Montana, but we may not be able to generalize the results to the entire United States since it is, at the university, conducted by the University of Montana. We'll have to see. We'd have to know more. Expected counts greater than 5. From the expected matrix created by the CAS while conducting the test, we got 43.66, 40.54, and so on, all greater than 5. You could also take the row total times the column total and divide by the grand total, and you should get the same value. Okay, and again, you do this in your calculator just like you did for the test for homogeneity. All right, we're going to find the p-value of our test. So we're going to use, again, the same steps. You get a p-value of 0.0884. So let's do our conclusion. So due to our large p-value of 0.09, we fail to reject the null hypothesis. These data do not provide evidence of a relationship between political association and gender. All right. So that is it for this lesson. I will see you in class. Make sure you do the problems to try on your own. Thank you. Have a good day.